to the IARPIC Atmosphere Collaboration Team meeting for May, and it's great to see some new faces here. So thanks everybody for dropping introductions into the chat. For those of you who don't join us regularly, we do have monthly meetings with the Atmosphere Collaboration Team as we do our best to highlight and support efforts that are aligned with the Arctic Research Plan. And we are, of course, transitioning to a new Arctic Research Plan in the coming months here, but great to see efforts that kind of span those two plans. And ALPACA is certainly a really nice example of work that impacts or connects to many of the different elements of both the former and the new research plan. So for today's meeting, we have an overview of the recently completed ALPACA campaign with some initial highlights and updates on how things went. This is a very exciting campaign for me. I know there's a lot of good research done, and we're excited to hear more about it. So I think given the potential length of the presentation here, we will just jump in. And I saw the slides quickly. I don't know, Jessie, are you starting out or is Bill starting out?
I'm going to show, but Bill's going to speak first.
Okay, perfect. So I'll first introduce Bill Simpson, who's from UAF, and he was the primary PI and coordinator for ALPACA, and he will lead us in and I think hand off the presentation to some of the other ALPACA participants along the way. So Bill, thanks for joining us today. Welcome, and we look forward to hearing more about how the project went, or how it's going. I guess it's still ongoing.
Yeah, great. Thanks very much, Heis. Can everybody hear me? And you're seeing the slides by Jessie, so great.
Yes to both.
Great, thanks. So I really appreciate the chance to share with you what we've got as first results from the Alaskan Layered Pollution and Chemical Analysis, or ALPACA study. And we're going to have 3 talks today, or 3 sub-talks by Jessie Creamean and Jochen Stutz and Peter DeCarlo. This is, of course, all work that is enabled by the great efforts of the ALPACA team. You can see logos of the some 20 institutions that were involved in the study. And I also wanted to thank the other people who were co-hosts, specifically Javier Focasato is here, and then Jinchu Mao, who's also a professor here. We were the 3 organizers for 3 of the sites that were being used here in Fairbanks. So could we go to the next slide, Jessie? Thanks. So the first question we really need to think about is why do northern cities like Fairbanks have a wintertime air quality problem? And one of the most key things is really strong temperature inversions. And these temperature inversions tend to trap pollution near the ground. That's coupled with the fact that we have a lot of ground level and some elevated sources of particulate pollution. So driving, heating, power generation all produce particles, and they're going to be an issue here. Additionally, it's very cold and dark, and those are different conditions than you usually have in an air quality study, and that may promote particle formation or ice fog formation. So these are big questions to understand air quality in northern cities. Next. Additionally, we've been having an air quality problem here in Fairbanks for quite a while, and we've heard a lot of community questions, many of which were not answered by previous studies. So another goal we have is to understand answers to community questions. One thing that the community asks a lot about is how do power plants affect us at the ground level? So you can obviously see emissions from the power plants, like this plume here that's aloft, but how often does that actually get to the ground? That's a big question, both regulatory-wise and from the public's point of view. Another question is, people are indoors lots of the winter time, and what are they breathing in that indoor air? How is the air quality indoors compared to outdoors? And then a third question stems on the fact that there's a lot of sulfur in the heating oil that's used in Fairbanks. There's also sulfur in coal that's in power plant fuels. So a move that's afoot right now is a change to reduce the sulfur in the heating oil, go to lower sulfur heating oil to try to clean up the particulate pollution. But we really want to understand the chemistry between the sulfur in the fuel and the sulfate that ends up in the particles. So these are key local questions that we hear here in Fairbanks and want to address. Fairbanks has had a history of really bad air quality, both in the winter, that's our subject in ALPACA, and in the summer during wildfire events. We often have hourly PM 2.5 concentrations exceeding 50 micrograms per cubic meter, and that of course exceeds when in a 24-hour average 35 micrograms per cubic meter, and we do violate that 24-hour PM 2.5 standard, unfortunately, here in Fairbanks. Additionally, we have multiple of those power plants that we talked about around the area, and we want to understand their impact on ground level air quality. There is residential wood burning, both in outlying areas around Fairbanks and in Fairbanks itself, and that can lead to a source of particles right at ground level and is a contributor to bad air here in Fairbanks. And then this all comes into this question of the very shallow inversion that we have over town. So next one. So we designed a study, and a picture from the white paper is being shown here that has both the field study we'll tell you about today and then modeling and laboratory studies. So you can see all this, and you can go to our white paper to find out more about this. But really an important aspect of this is that as the Arctic warms, we expect there's going to be more development in the Arctic, and we really need to understand pollution in the Arctic to have good practices for rational development of Arctic locations as that happens with a warming climate. Next one. So just a quick overview of the field study. It occurred in January and February 2022, just this past January and February. And there were more than 40 researchers who came here to Fairbanks and 20 institutions, and you saw them on the first slide there. Next point. Really, this was some of the most state-of-the-art measurements that have been done in Fairbanks, and we had 3 main sites. And in the interest of time, I'll let the next I'll let Jessie start off with the introduction on that after. I would like to thank our funders. NSF generously funded this project through multiple grants. NOAA had a lot of funding for us also, and international funders contributed major components to this. And of course, we're in collaboration with the Alaska Department of Environmental Conservation and the EPA, who provided a lot of collaboration and in-kind contributions to the project. Really, the issue here in Fairbanks is not just an issue of understanding the chemistry, but really what to do about it. And we need to have social studies, social science studies to understand the societal context to this. So another component of the ALPACA project is social science and community engagement. And you can see public events at our website. And as we get these results and bring them back to the community, and work with the community to try and figure out appropriate solutions, we'll continue this collaboration with the community. So with that, I think I'll hand it over to Jessie Creamean, who is at Colorado State University and was a key researcher in the study here, and will tell us about one of the sites.
Cool, thanks, Bill. Can you guys hear me? Yeah, cool. Okay. So as Bill had mentioned, we had a few sites throughout Fairbanks to kind of understand 3 main themes or concepts that we were focusing on for ALPACA. So the first one being, if I can get my clicker to work, there we go. So outdoor air quality. And one of the main sites that we really focused on this was at a location called the Community Technical College, so CTC, and that was in downtown Fairbanks. We also had a focus on indoor air quality, and these measurements were done inside of a house in a neighborhood just outside of downtown Fairbanks. And then we also had vertical profiling measurements. So these were done both near the downtown sites, and then also you can see on the map here, far outside the town at the UAF experimental farm fields. So I'm going to specifically focus on measurements that were done at the downtown site. And so here's an overview of the various measurements that we had. You'll see all the little logos to show who kind of did what. So you can really see it was a really collaborative effort to be able to manifest this comprehensive set of observations. And so in this picture on the right, you can see 2 containers, the blue and the gold one. That is where most of our measurements were. And then I'll show a picture on the next slide, but we also had some measurements vertically on the CTC building so we could look at profiles of different gases and meteorological measurements. Generally we had a bunch of trace gas measurements that were mostly in the containers and some on the CTC building. We had a whole host of aerosol observations, so focusing on mass concentrations, which were conducted at the ground and higher up. We had extinction measurements, so aerosol absorption and scattering. We had measurements of aerosol number concentration and size distributions, a bunch of different chemical measurements. So those include real-time measurements, in addition to filter collections for offline measurements of chemistry. And those also include bulk measurements and single particle measurements looking at the size, shape, and the chemical composition of individual aerosols. We also had measurements of different ions in aerosol samples, different isotopes, and then ice nucleating particles or INPs, focusing on those aerosol ice fog interactions. And last but not least, we had meteorological measurements at the ground, but then also along the profile of the CTC building. So we'll jump into some really preliminary data of some of the meteorological measurements during ALPACA. So on the left here, you can see a picture of the CTC building. And this picture was obviously not taken in January or February. This much nicer weather. We had like 3 inches of ice and 3 feet of snow on top of that during ALPACA. And it was dark, of course, for most of the time. But this is showing the building. And then these numbers on the right of it indicate the different levels at which we had some measurements at. So this top plot here is showing the wind speed that was measured on the ground, colored by wind direction. And you can see that most of the time, the wind speeds were relatively calm during ALPACA. So less than 2 meters a second, that's pretty calm for a high latitude region. And that's, as Bill was saying, you know, Fairbanks is kind of in a valley situated between hillsides. So we really don't get a ton of strong winds there, except for an occasional storm here and there. On the bottom plot, you'll see the temperature difference between the measurement at 23 meters and then the measurement at 3 meters. And you'll see a dashed line at 0, indicating there's no temperature difference. But as you can see for pretty much almost the entire study, we had warmer temperatures aloft, and you'll see cases where we even had an upwards difference of 5 to 10 degrees C, indicating really strong inversions that Bill was talking about. So we really have these pretty often, and this kind of demonstrates that in Fairbanks. So those inversions really affect the composition of the atmosphere under those inversion layers. So in blue, here's that same temperature difference, and then in orange is showing carbon monoxide concentrations. And you can see that they track pretty well. So especially when we have those really strong temperature differences or inversions, that's when we have these higher concentrations from the surface sources that are building up and collecting in this really capped shallow layer near the surface. This also affects particles in addition to gases. So here's looking at some related species in the gas phase and the aerosol phase. In the blue dots, you'll see nitric acid gas phase concentrations. And then in the light blue line, you'll see nitrate concentrations that are particulate from aerosol. You can see they track pretty nicely because they're related in terms of their heterogeneous chemistry. But again, during those inversions, we see higher concentrations, and particularly during this late January, early February time period. Now, the composition of the air can change during these inversions, but also so does the quantity of particles and the size of particles in these inversions. So the top plot here is showing total aerosol concentrations from number concentrations that have diameters between 10 nanometer and 10 micron. And then on the bottom plot in the dark green markers are the 15 to 60 nanometer particles in terms of number. And the light green line behind shows the mean particle size within this size range. And so you'll see again that when we have elevated concentrations, those tend to be during those inversions. Sometimes we get little spikes, and that's just from local point sources. But what's interesting is that the concentrations increase, but also so can particle size, particularly during this late January, early February event. And that's due actually to an ice fog event, which I'll talk about in a little bit. We have not only the inversions, but other interesting features or processes that can affect the composition of the air in Fairbanks. So here's a plot showing ozone concentrations in black and particulate mass concentrations in orange. So this is mass for particles that have diameters of 10 micron or less. And you can see that they're almost anti-correlated. And so this PM is higher when we have those inversions or ice fog events, but it's opposite of the ozone concentrations. And one might think, oh, ozone's a pollutant, we should expect that to build up during these strong pollution events. But actually, when we see the highest concentrations, that's when we had snowfall events. So you have these systems come through, they can drive mixing in the lower atmosphere and actually mix ozone down from higher up, versus during the inversion events when we don't really have that process happening. So I've mentioned this time period a few times, and that was my focus during ALPACA, was this ice fog that Fairbanks gets traditionally. And so ice fog is a fog that consists of really fine ice crystals that's suspended in the air. They're almost always present at about less than minus 40 C in Fairbanks, as long as there's a persistent source of water vapor. But these ice fogs have been observed up to minus 15 degrees Celsius. They typically exist under clear, really calm conditions with those steep inversions. And it can cause a lot of issues with air quality. So not only can the pollution have health effects and hazardous transportation effects, but so can this ice fog. You can see in the background picture here, that is an ice fog, example of what ice fog looks like. And so you can see it gets pretty hazy. And the interesting thing about ice fog is you really need aerosol particles to help form it, unless it's super, super cold, where water can kind of just form on its own. But because Fairbanks is so polluted, the particles are there for the water to condense and freeze on. So our group at Colorado State, so I had a project with Russell Perkins and Paul DeMott, and then our graduate student, Emily Lill, who did most of the work. And then our colleague, Ezra Levin from Handex Scientific. We focused on this one key question of what role do combustion products, including organic and inorganic aerosol, play in terms of seeding the formation of these ice fogs? So we had a bunch of different measurements at the CTC. These included measurements of real-time particle mass and metal concentrations, aerosol number concentrations, real-time ice nucleating particle concentrations. We also had collection of samples for offline analysis of aerosol chemistry, shape, and size in collaboration with Carrie Pratt from University of Michigan. And then we also had offline samples collected for size-resolved ice nucleating particles. And we also, last but not least, had a mobile package that had a few miniaturized instruments, including a MET station. So you can see Emily Lill in this top upper right picture here with both of those instruments that we would deploy above the ice fog so we could compare aerosols and meteorology from above it to within it. And we weren't too surprised, but it was still shocking to see how dirty the air is. So this picture here is showing an example. Each of these streaks represent a 24-hour sample. So you can see just like how dirty the air can get there. And so we definitely have more than enough aerosol to work with our offline samples. So here's a plot I already showed, but it's the PM concentrations with the ice fog period highlighted. And so this particular period, particulate mass increased by about 160% relative to the non-fog periods, even when we had other stronger inversions. So this ice fog event really had a strong inversion, and we had all this extra stuff that was in the air due to the formation of these ice crystals. Just a quick initial result. So we looked at the metal concentrations during these periods. And so here you'll see concentrations of different metals on the bottom axis. The blue bars indicate non-ice fog periods, and the gray bars indicate ice fog periods. And you can see that the gray bars are typically higher than the blue bars for each of the different chemical species, indicating that the abundance of these different metals was higher during the ice fog events relative to the other periods. So some of the next steps for us are going to be to look at the ice nucleating particles, see if those change over the course of the event, and then look at different cooperating data sets like aerosol composition, number and size, and also some trace gas information. So with that, I'll go ahead and hand it over to Pete, who's going to be talking about the house Supersite.
Thanks, Jessie. Can everyone hear me? All set? And you can see? Good. All right. So I'm moving on to kind of combining outdoor air quality and indoor air quality at the house Supersite. And so this was the subset of researchers located at our house site, and kind of a blurred out picture of us huddled around the pellet stove and talking science, which was kind of fun to do. I want to start off with when I arrived in Fairbanks, kind of put everything in perspective for why we were there. This is the Dark Sky app on my iPhone. When I got off the plane, it was -14 outside, which means that people were probably inside and not outside. And this was one of the more mild temperatures that we experienced while I was in Alaska. The next thing you see is there's an air quality alert. And air quality regulations are in place for outdoor air quality, but we don't have any way to regulate indoor air quality for a host of reasons. And then finally, if people are inside and we don't have regulations, what are the processes that impact indoor air quality, whether they be outdoor getting transported to the indoor environment, emissions in the indoor environment, and how temperature and relative humidity differences between outdoors and indoors can impact things like particle composition or gases in the air that we're breathing. So we went about this, we brought a team together to look at detailed chemical composition measurements of trace gases and particles, both inside the house and outside, so that we could understand things like how much of that outdoor pollution that Jessie talked a little bit about makes it inside where we're spending the majority of our time. Also, we're talking about 50 degrees centigrade temperature differences between outdoors and indoors. When that outdoor air pollution comes into the indoor environment, how does that impact the composition of particles? We know that a lot of particulate matter has semi-volatile components, and 50 degrees C is a huge change in environment. So the volatile components that may be condensed outdoors will volatilize indoors. And then also in terms of what people do in their homes, a lot of people are using biomass to heat. So we had a pellet stove installed in the house that we were making measurements in. And Bill was incredibly instrumental in making all of this work out. And it gave us a chance to see, when people fire up a pellet stove in their home, which should in theory be a little bit cleaner than a logwood stove, does that impact the indoor air quality? We also have to eat. And it turns out from many different projects that I've been involved with, cooking is one of the major sources of indoor particulate matter. So how does that impact and interact with outdoor air pollution that gets transported into our indoor spaces? Excuse me. So the laboratory at the house wasn't trailers, it was a garage. The garage door you can't see here was replaced with paneling, so we could stick inlets out the window. And you're seeing a subset of all the instrumentation that was in the garage, the PTR TOF-MS from the University of Montana, Brent Williams group with the SV tag instrument. You have some trace gas instruments. Behind here is the University of Michigan single particle measurements with their ATOF-MS, and then our SP-AMS pictured in the foreground. I'm going to show some quick look results from the trace gases and the AMS, and just see how we can start to answer some of the questions that we have about outdoor and indoor air pollution. So in order to do these measurements, we need a way to switch back and forth. This is our valve switching system, and we were doing 10 minutes of sampling outdoors and 10 minutes of sampling indoors. So over the course of an hour, we're getting about 30 minutes outdoors and 30 minutes indoors. Means we get an outdoor data set and an indoor data set to play around with, which we have about twice the data to work with now. And the measurements of things like carbon monoxide and methane look something like this. We can start to separate them into the outdoor component and the indoor component, outdoor being the darker color here, indoor being the lighter color. And what you see is the outdoor concentrations are a little bit more up and down, and the indoor concentrations are much more smoothed out, and there's a lag between what you see outdoors and what you see indoors. But overall, for things that don't have chemical loss processes, the average concentration indoors is roughly the average concentration outdoors if you look at the whole of the campaign. So sometimes CO is higher inside, sometimes it's lower, and similar with methane. What we're interested in from a health perspective, and building off what Jessie talked about, particulate matter is something that we're really concerned with from a health perspective. It tends to drive most of the health effects that we look at when we think about air pollution. And so the gray color here is the outdoor concentration that we measured with the AMS. We got some very high concentrations, and this is preliminary data, so things are subject to change. This is field ready, not 100% QA/QC at this point. But in general, indoor concentrations are quite a bit lower than outdoor concentrations, except for when I have these red arrows here. And these red arrows are when we had an activity inside the house. And so this case, when we have a pellet stove or cooking activity, we see concentrations that are higher indoors or roughly the same as outdoors in those two instances. But more importantly, we can start to separate things into chemical species and chemical components. And so the top graph here is the separation of the different chemical species in the particulate matter from organic, sulfate, nitrate, chloride, and ammonia over the course of a few days in February. And then the indoor concentration and composition. So they're on the same scale, and you can see that decrease in the indoor space. And you can also see back where I had those arrows. These are when we had the pellet stove turned on. And so you can again see these increases in concentration in the indoor spaces. And keep in mind, this is, while there's an air quality alert outdoors for some of this time, what we're seeing in the house, and this isn't necessarily going to be every indoor space, but in the house where we're making the measurements, the concentrations are quite a bit lower and the composition is different. So one of the things that we like to understand in these types of experiments is how fast and how much of the outdoor air pollution comes inside. And that's a complicated question, again, with the temperature gradients and the relative humidity gradients. And so we like to take a step back and think about things like sulfate, which in theory is a non-volatile tracer for outdoor pollution coming indoors. It's not quite 100% true in this case because we are noticing that there is some sulfate emissions from the pellet stove. But if we're not using the pellet stove, we can use sulfate to trace what's coming in from outdoors, and we expect it to mostly be lost through deposition in that transport from outdoor to indoor spaces. So the outdoor concentration is higher and more jagged. The indoor concentration, smoother, lower concentration. What we can do is do a time series shifting analysis to see when those two time series correlate the best. And that gives us an indication about how long it takes for a plume of pollution outdoors to be reflected in the indoor environment. And what we find is if we shift the indoor data set by about 40 minutes, we get the best correlation. And so it takes about that much time to turn over the air in the house, and we start to see that air pollution from outside coming in. The other thing that correlation analysis allows us to do is get a slope, which is the rough relationship between the indoor concentration of sulfate and the outdoor concentration of sulfate. And the slope of this comparison is about 18 or 0.18. So 18% of the sulfate outdoors essentially makes it into the indoor environment. So we're losing about a factor of 5 of that air pollution in the indoor environment for a non-volatile component. For a component that is volatile, that temperature gradient may impact it beyond that mechanical loss or that depositional loss that we're seeing for sulfate. So we can average across the campaign and we can say, okay, what does typical outdoor for this couple months in the early part of this year, January and February, look like outdoors? And that's what you see in this stacked bar plot. And then the corresponding indoor concentration. This is when we aren't cooking or burning anything in the pellet stove. When we're cooking or burning something in the pellet stove, the overall concentrations are relatively similar, but the composition is different. Both cooking and pellet stove activities added a significant amount of organics, but not a lot of other chemical species. And so in general, the compositional change is important to think about as well. We can look at time of day and compare outdoor and indoor concentrations as a function of time of day. And so you can see kind of typical morning peaks and afternoon peaks. This is more corresponding with the few hours of sunlight that we have during this time period. And then overnight, the organics peak a little bit higher, and there's not much of a sulfate peak later. So we can start to tease apart the time of day compositional changes in the aerosol and see how that may be reflected in the indoor environment as well. The final thing I wanted to touch on is because we have mass spectral data, we can actually start to look at compositional differences in more detail. And so what we can do is we can look at this time series where we are looking only now at the indoor composition using the mass spectra that we measure with the aerosol mass spectrometer. And we can say, before we start doing anything, this is what the average mass spectra looks like for this gray period that you're seeing right here. Then we turn on the pellet stove. We want to warm up the house a little bit. And we can see that the mass spectra changes. We see these increases in some of the organic peaks in our mass spectra due to that. And then we get hungry. We want to cook something. And so we cook something right after that. And that's going to layer on top of the background, the pellet stove, and now we're adding cooking. And when we do that, we get, this third mass spectrum. We're starting to see more peaks pick up over here. And so we can very clearly see the compositional change in the particulate matter as we do these different indoor activities, thinking about how that may impact health, and linking up with some of the groups who are looking at things like reactive oxygen species in the aerosol and trying to understand, do these compositional changes matter in the context of human exposure and health? So this is just a really preliminary look. There's going to be a crazy amount of results coming from all these different groups because everyone has 2 data sets to play with. And we can compare the outdoor air quality and the indoor air quality in both the gases and the other particles. So I'm going to turn it over to Jochen at this point.
Thanks, Pete. Can you see my screen? Yep.
Yes.
Okay.
Yes.
Thank you. So I'm going to, move on to, we call this vertical measurements, and I'm going to look at this a little bit more complex. I think Jessie and also Bill already gave an intro on how important the vertical structure of the atmosphere is and how important mixing is. But I like to look at this more as a complex system of chemistry and transport, if you think about air pollution, that connects both the snow emissions, vertical transports, micrometrology, as well as aerosol chemistry. So Bill and I are involved in 2 NSF projects. That the first one, really the original kind of ALPACA project, really looked at sulfur chemistry and vertical mixing. And the big question is really, where's the pollution coming from? Is it originating from the ground? Is it coming from these biomass burning plumes? And also the other aspect was sulfur chemistry. And so the second project, and Jack Dipp, who's online, is involved in this, is really understanding sulfur chemistry, because the textbook knowledge that you learn in school about air quality says that you take SO2 and you have to convert it in liquid water droplets or OH chemistry, and then for OH chemistry you actually need sunlight, which you don't have in winter. So while we have these different questions here, I'm just going to focus right now on the question of vertical transport and vertical structure of the atmosphere and where that pollution actually is in Fairbanks. And the motivation on a very basic level really is that obviously we live in the lowest 20 meters. When you're in LA, in a big city, maybe you can go up to a skyscraper, but generally we're living at the ground. And so that is where we get exposed. And here is a temperature profile from the airport in Alaska. And you see that these extraordinary strong temperature inversions that Bill and Jessie already mentioned really are just right at the surface. And if you go higher up, those inversions aren't as strong. So we really wanted to understand much better how those are accumulated in the surface layer, as well as the question is, how are they mixed upwards and or downwards? I mean, one of the theories is that the power plant plume is mixed downwards to the ground, and that is the source of sulfur. And then what I'm not going to talk about, which is something we're working on, is really the role of snow, and as well as all the chemical mechanisms of that influence sulfur chemistry. And so Bill's group and my group set up a system in downtown, and the downtown is a white word. We set up a long path DOAS system, and I'll explain that in a second, to scan over where the houses that Pete described. But the 2 parts of this was what Jessie mentioned earlier, the CTC building, where we had measurements, in situ measurements at 3 meters altitude, a meteorological mass that gives us temperature gradients, as well as some measurements on the top of the building. So that just covers the lowest about 20 meters of the atmosphere. And what my group added to that was a so-called long path DOAS system. And I'm just going to switch over really for 1 second. We don't have a lot of time to explain this. And it's basically an open path absorption instrument that shoots a light beam through the atmosphere, catches it, and then does spectroscopy to measure trace gases. And so what we do with these systems, we set them up so we can scan through the atmosphere, and that way we can reach above the 20-meter level. And the limit for us is how high we can hang our reflectors. And in this case, Birch Hill allowed us to go up to 200 meters. And this is typically an area of the atmosphere that's very difficult to probe. And so what we do is we take this instrument, we scan sequentially on these different levels, and that gives us information of the composition of the atmosphere above that surface layer, and it gives us an idea of how mixing works. So the first thing I'm going to show is some data that Jessie already has mentioned, is the CTC building information, where at the top level here you see CO2 measurements, and you see these really strong gradients in CO2, where you go from a background level of maybe 400, 440, 430, and then if you go at 23 meters, and if you go at the surface, you can have easily 500, 600 ppm of CO2. And those levels here typically coincide with very strong temperature gradients in surface inversion. One of the interesting parts really, and I'll show some more data in this that you can already see in this data set, these inversions are usually associated with very low wind speeds. And the second the wind picks up, and we're not thinking about, although this one's a pretty high wind speed, I have to say, I'll show much lower ones. Even if you go from 1 to 2 meters per second, the atmosphere starts to mix. And then pretty much instantaneously, these gradients disappear. And these are the events that we were actually really also interested in seeing how often does this happen and what does it do to the atmosphere. So our measurements and Bill's measurements, really the main focus was on the main pollutants in Fairbanks. And I'm showing two graphs during one of the periods where we had some of these very strong surface inversions. And I'm showing this mostly just to give you an idea how strong these gradients are in these lowest 200 meters of the atmosphere. So I'm going to have a color code here. So for us, the pinkish color, magenta color is the in situ measurement. So this is 3 meters. Black is between 15 and 20 meters. Blue is 20 to 78 meters. And then red up to 120 meters and green up to 200 meters. So what you can really see here for NO2 and also for SO2 is that most of the levels in these lowest 20 meters are much, much higher than what is above 20 meters altitude. In some occasions where you see that the SO2 aloft is a 1-2 ppb, and at the surface at 3 meters, you have 20 to 30 ppb of SO2. So really stark differences. That is, however, not always the case. For example, for NO2 here in this earlier period, you can see that the entire lower 200 meters actually are fairly polluted. And so one of the things we are looking for is really trying to understand some of these events where it's also mixing upwards, as well as the events where you have these really, really strong vertical gradients between these two sides. So as was mentioned earlier, this is an overview over the first 3 weeks of the campaign or so, where the top graph shows the temperature inversions between 23 and 3 meters. And then you see in situ measurements that Bill's group did at 3 meters, NO, NO2, and NOx. And then on top of that here, the long path, there was NO2 values and the SO2 values. And I think this is visually, I like this plot because it really shows how whenever you have surface inversions, you actually have these gradients. Actually, what you're probably focusing on is the times where you don't have gradients, which are these gaps here where pollution levels really drop, and here as well. And again, this isn't always the case. Here's a period where we actually have these very strong where the gradients aren't as strong. You can have very high pollution levels even aloft. One of the things that, is kind of interesting with this data set is looking at these mixing events. So what happens when you have an event where your gradient disappears? And so I zoomed into one that happened on January 29th, where the top is wind speeds, so very calm conditions, below a meter per second wind speeds. You have a temperature inversion of 2 to 3 degrees centigrade, and you can see 100 ppb of NOx, 40 ppb of NO2, 15 ppb of SO2. And then, this is from 3 p.m. To 6 p.m. Alaska Standard Time. And you see the wind speed just increasing by about a meter per second, just a very slight increase. I think many other conditions that would still be considered calm, but for Alaska, for Fairbanks in winter, this is actually real wind. And you can see the second this wind goes up, the inversion starts to disappear. And you can see how the concentrations at 3 meters really drop pretty quickly. It looks really kind of like an exponential decay. And what happens at the same time, both for NO2 and SO2, is actually that the concentrations of these two species aloft are actually going up at the same time. And so the interpretation of this is clearly upward mixing that happens under these events. And that's how you mix this. What I find the most fascinating part of this is actually when this ends, how fast you can actually fill up that boundary layer again. And within an hour or two, you reach back to these levels that you had before. So this is a very dynamic, fast changing environment. I wasn't going to do a lot of chemistry, but one of the questions we were interested in is there a radical chemistry during the daytime chemistry in Fairbanks? And there's only really one component we know that can make OH radicals, and that is nitrous acid. HONO photolyzes even in wintertime because its absorption is far enough in the blue that it's efficient. And so we actually saw these very high levels of nitrous acid near the surface. And so that basically means that there is photochemistry going on even in January when you only have about 6 hours of daylight. And that's something we were very interested in, and something we want to look into much more detail and deciding how important that really is. So just to kind of sum up, we saw these very strong profiles of pretty much any pollutant we can measure over this 5-week period. It's always associated with surface inversions, and the wind speeds and any meteorological condition that has higher winds will lead to a mixing of this. So there is a very strong connection to how well we can describe the metrology. And then just the outlook, this is a very great data set with a lot of information, and trying to study this kind of complex metrology pollution system is going to be really exciting and really really interesting. And I think with this, since I'm the last one to speak, I want to thank everybody for listening, and I hope we left some time for questions.
Excellent. Yeah, thank you very much, Jochen, and everybody for this really nice presentation and overview of the ALPACA campaign. There's a lot there. I already see Jack has a hand up. Jack, go ahead, please.
My question, I think, is mostly for Jessie, but maybe a combination of Jessie and Jochen. But I was curious, Jessie, how you actually define the ice fog periods, because it seemed when you showed us the graphs that you were suggesting that entire 6-day period at the end of January and February was an ice fog event. And I didn't have that impression being there. And also, I just noticed that Jochen showed a lot of DOAS data throughout that exact period. And the DOAS doesn't like ice fog very much. So I'm just curious. I don't think we had 6 solid days of ice fog ever in Fairbanks.
No, it wasn't that bad. So we were getting daily specialized ice fog forecasts from the National Weather Service. And so this one was not as dense as like the one that I guess Fairbanks got right before we got there for ALPACA, unfortunately. So it was a pretty light one, and it was intermittent during that time period. So I just showed generally that's the period, but it's not that ice fog was persistent throughout that whole time.
Yeah. But I guess my question though is, when you showed the difference between the abundance and the composition of the particles, was that over those 6 days against, or did you have some kind of filtering within that to say how thick was the fog and relate that to the particles? Yeah,
that was just the 6 days, because we don't have information on the fog thickness. Unfortunately, I had a probe that was supposed to measure water and ice content, but it was so cold during that period that the battery consistently died, even with hand warmers in it and trying to insulate it. So we have some data throughout that period that we might be able to use to determine how icy or how much ice content or water content or super cooled liquid water content was present during the fog. But right now we just have from the forecast information. Does that answer your question, Jack?
Yep, thank you.
Okay. Excellent.
Additional questions? I have one. I thought I saw, Jessie, in your slides, I think it was in your slides, you were talking about, the inversion strength and the wind. There was one figure where it had a time series of both. And in that figure, it almost looked like there were stronger inversions when there was wind present, which didn't make any sense to me. And I was going to ask you about it, but then Jochen showed the opposite. So that makes more sense. But maybe we can revisit that slide. I'm just curious as to whether I missed something in that image or not.
Let me pull it up again really quick.
This is the one with, there was like a color
Yeah,
coded
here, let
time
me,
series of the, yep, that's the one.
that.
So there, I mean, it looks like the increases in wind speed are kind of coincident with the strongest temperature differences, and maybe I'm misunderstanding what the temperature differences
They're
represent.
kind of, yeah, they might just be slightly after, and that's what breaks up the inversion. That's kind of what Jochen was talking about. So it might be hard to see on this time series because it's expanded to the beginning of January. But if you're looking a little closely, the winds start to build up and then they kind of shift direction. It looks like after the peak. I don't know. I'd have to look more closely. I just paused these yesterday, but
Okay, I mean, that certainly makes a lot more sense to me, that wind-induced mixing would kind of mix out the inversion. But this particular plot just made it look like the biggest spikes in the top plot and the biggest spikes in the bottom plot were kind of co-located.
yeah, I have to look more closely, but yeah.
Okay, thanks. It looks like Javier has a comment. Javier, go ahead.
Yeah, hi, thank you guys. Just one thing actually. When we talk about inversions, actually, I think that the value that you're plotting is the stratification, the delta T. So the height of the inversion, which I think is the more challenging element here to look at, because you can be at an inversion that is 150-meter height, or you can be at 350-meter height. That's the height of inversion. That's the capping inversion. But also stratification layers, or stratified layers, are also capping inversion. More often when people see here, oh, the plume that is hanging around, and they say, oh, that's the inversion, but it's already 9 p.m. The inversion is at 300 meters. So the trapping is just in the first stratified layer. So I think that beyond the delta T, which is the stratification level you have, obviously as the stratification level rises, it means that you have a radiative cooling that is building up a strong surface-based inversion. So we all agree on that. But the height of the inversion is the air mass, or we give you the air mass that you are integrating within your whatever delta time that you're averaging your measurements. And I think that is another element that we should work on, that because that is significant. Now related to Jochen measurement, these are really very interesting. Normally, under anticyclone conditions, if you have a pulse of winds, actually would be a sort of a momentum imbalance within the valley, and not necessarily, when you talk about 1 meter per second, 2 meters per second, even to 3 meters per second, still the pressure gradient across the plains could be negligible. So that basically you are under non-advective conditions. So therefore you are still local. Okay, just to say that that although here probably it is important, I will say that in the lower 48s, 1 meter per second, is still kind of blocky condition, But it is important in the short scale of the 10-kilometer probably air mass that we are looking here in Fairbanks.
Yeah, but it's a very common condition in the Arctic. I mean, this is not. Yeah. I mean, this is nothing that people haven't reported, right? These extraordinarily strong inversions.
Oh no, yeah.
I think the surface, the stratified surface layer, how you call it, and we chemists call it surface inversion. It's just a really common feature in the Arctic, and I think underlying phenomenon that regulates a lot of the surface atmosphere interactions that relates to ozone depletion events in the troposphere. It relates to how you interact, how you get trace gases out of snow into the atmosphere, and so on and so on. And I think you would agree this is not something that we know how to quantitatively describe really well.
Oh, no, no, totally. And actually, you know, that's why we moved here 20 years ago, actually, because basically the problem is about the turbulence in the very weak turbulence levels, the very low, shallow layers. You know, everybody can measure at 3 kilometers, you know, with LiDARs and whatever other radio sounding, but the lowest levels are the more difficult. Yeah, of course. Yeah. Anyway.
All right, thank you. Yeah, there's also a nice discussion going on in the chat on the side. I'm not sure how people are keeping up with both, but there was a question from Santiago about the winter signature for organics from the forests and whether there was anything going on there, whether that was kind of dormant. And from the initial responses, it sounds like people are assuming it's dormant, but it hasn't been verified. Any other comments on that? Otherwise, I see Chuck's hand is up as well.
Yeah,
Chuck, go ahead, please.
Thanks. I just wanted to comment that given the inversion strength and lack of mixing, and when mixing does occur, how dramatically things change, that normalizing to CO for everyone's measurements is going to be much more important than just looking strictly at concentration levels. And then the other comment I wanted to have was, it was just a curiosity. If I were a settler building a house in Fairbanks, I would want to build up on the hill and avoid the cold air down there in winter. So I'm surprised that the city of Fairbanks developed. I know it's in proximity to the river, but I'm surprised that so much of the residential area is down in the lowlands next to the river and not on the nearby hillsides where it could be 20 degrees warmer in winter.
It's a really interesting point, Chuck. And not living in Fairbanks, I don't know the history of that, but I wonder if anyone from the local community has any particular response.
Can I say something related to that?
Yeah, go ahead.
People here says yes because of that. Actually, people say, "Oh, you have to go and live in the hills above the inversion." But actually, meteorology, that is the cold layer. So you want to live just underneath the inversion, which is the warmest part, actually. And yet, yeah, that's what we do actually. Normally, you have like 15 degrees Fahrenheit, actually warmer in the hills around the city. Now, yeah, go ahead.
I was just going to say, historically, Fairbanks developed at a time when, 100 years ago, when you wanted to be closer to where you worked and, everything was down by the river. So the development has gone outside of town now, and a lot of people living higher up. But still, there's a lot of people who are living down in town at this stage, just kind of historically. And I mean, it is nice to walk around. It's more of a city if you're looking for a city environment.
Just to add, my group had some mobile measurements, and driving up the hills was not pleasant when there was a lot of snow on the ground. So there is a benefit to also being where they plow and not high up in the hills.
All good points. So we're at the end of our hour, roughly. Any last comments or questions? Okay, well, if not, I want to thank everybody for being here, and thanks to the speakers for providing a really nice, interesting presentation to the group. This was recorded, as you know. It will be posted online, and we typically do get quite a few, after meeting views. So hopefully there will be some additional follow-up from that. Next month, we plan to have a meeting that's focused on the Northern Alaska observatories, some evolution there, and kind of catching up with the different entities involved with maintaining and running those observatories. So hopefully many of you can join us again a month from now. Thanks everyone for joining. Meredith, anything else from your side?
Just that, yes, the meeting was recorded and will be available by the end of the day, Thursday.
Thanks.
Great, thank you, Meredith. All right, well, thanks everyone. I hope you have a good rest of your week. We'll talk again soon.
Thanks, bye.
Bye.
Thanks.